Reciprocal function.
The reciprocal function is also the multiplicative inverse of the given function.
This is in the equation y equals 1 over x or f of x equals 1 over x.
Let's try assigning values to x, starting with x equals 1.
So 1 divided by 1 is 1. So f of 1 is 1.
Let's try assigning 10, so f of 10 equals 1 divided by 10. 1 divided by 10 is 0.1.
Then we are going to try 100. So f of 100 equals 1 divided by 100, which is equal to 0.01.
Then we are going to try 1000, so f of 1000 equals 1 divided by 1000, which is equal to 0.001.
Then we are going to try smaller numbers, example 0.1. So f of 0.1 equals 1 divided by 0.1, which is equal to 10.
Next is 0.01, so f of 0.01 equals 1 divided 0.01 is equal to 100.
As x increases, f of x decreases, and vice versa.
Let's try -1, so f of -1 equals 1 divided by -1, which is equal to -1.
Then -10, so f of -10 equals 1 divided by -10, which is equal to -0.1. Then let's try -1000, so f of -1000 equals 1 divided by -1000, which is equal to -0.001. And if we try -0.1, so f of -0.1 equals -10. If we try -0.01, so f of -0.01 equals 1 divided by -0.01 is -100. Making table of values. If x is 1, f of x is also 1.
If x is 10, f of x is 0.1.
If x is 0.1, f of x is 10.
If x is 0.01, f of x is 100.
And so with the negative values. But here, we cannot have 0 because f of 0 is infinity. Using the values in this table, we have this graph. The x and y axes serve as the asymptotes with no 0 value. The domain of a reciprocal function is the set of x, where x is not equal to 0, and the range is the set of y where y is not equal to 0. Both the input and the output don't have 0. How to find the limit of a function as x approaches infinity.
To understand better, let's first have examples starting from 100.
Limit x squared as x approaches 100.
So it's equal to 100 squared, and 100 squared is 10,000. So the limit is becoming bigger as it is being squared.
Let's try 1000. So limit x squared as x approaches 1000. And it's equal to 1000 squared, which is equal to 1 million. And if we try -1000, so limit x squared as x approaches -1000. So it's equal to -1000 squared, which is equal to positive 1 million.
Using these values, we can say that as we limit x squared as x approaches very large numbers or to positive infinity, so we have a limit also of positive infinity.
And we limit x squared as x approaches negative infinity, the answer is still positive infinity.
It's because negative times negative is positive. This is also for all even exponents such as to power 4 or to the power 6.
But if we have odd power, example to the power 3 or cube, the limit is negative infinity. For polynomial functions, example limit x squared plus x minus 3 as x approaches negative infinity. For this case, we just consider the term with the highest exponent or power.
The other terms are considered insignificant.
So we have positive infinity.
And Clay Thompson just raised. And Clay Thompson just raised.
Another example, limit x cubed minus 2x squared plus x minus 3 as x approaches negative infinity. You consider here the x cube, and the others are insignificant. So we just go back to the limit of x with odd number exponents.
5 on the 24. Williams looking for help. Curry takes him off the dribble, gets inside. Layup is good.
The limit of reciprocal function and rational functions as x approaches infinity.
We know that f of 100 in a reciprocal function is equal to 1 divided by 100, which is equal to 0.01.
If we make this f of 1000, then it's equal to 1 divided by 1000, which is equal to 0.001. Here, as x becomes bigger, the value of f of x is approaching 0.
So the limit of 1 over x or a reciprocal function as x approaches infinity is 0.
By interchanging x and f of x, we can say that as f of x becomes 0, x is equal to infinity.
This is the shortest proof that the limit of x of a reciprocal function as x approaches infinity is 0. Example, the limit of 1 over 2x as x approaches infinity is equal to 1 over 2 times infinity, so it is equal to 0.
How about if we have a rational function?
Example, find the limit of 6x cubed minus 4x plus 5 over 2x cubed minus 3x.
In this case, find the highest exponent, which is x cubed.
Then multiply both numerator and denominator by the reciprocal of x cubed.
The numerator becomes 6x cubed minus 4x plus 5 divided by x cubed over 2x cubed minus 3x divided by x cubed. Simplifying, we have 6 minus 4 over x squared plus 5 over x cubed all over to minus 3 over x squared. All terms containing denominator x cubed and x squared are considered 0, so it should be eliminated. So the limit of 6x cubed minus 4x plus 5 over 2x cubed minus 3x as x approaches infinity is 6 over 2 or equal to 3. This is only applicable if the highest exponent are the same in both numerator and denominator, in this case x cubed.
The shortest way to solve this is to eliminate x cubed and the other terms, leaving 6 over 2 only. So the result is 3.
An example with different exponents in the numerator and the denominator is the limit of 5x to the fourth minus 3x squared plus 5 over 4x cubed minus 7.
Here eliminate 3x squared plus 5 and minus 7, but leave 5x to the fourth over 4x cubed, since they have different exponents. Then divide x to the fourth by x cubed, so it's equal to 5x over 4, and as x approaches infinity, this is also equal to infinity. Continuity and discontinuity of functions.
This is where we can apply the limit that approaches infinity.
This is the graph of y equals x squared, and this is a continuous function since there is no gap in the graph. For every input there is a corresponding output.
And here is the graph of y equals 1 over x. This is a discontinuous function since there is a gap in the graph at 0. 0 can make the function undefined. The y-axis, or at x equals 0, this line serves as the vertical asymptote, while the x-axis, or the line y equals 0, serves as the horizontal asymptote.